Hi, let's get started with our systems of linear equations or systems of equations. So when we talk about systems of equations, we're given more than one equation where we're looking for one solution, or at least that's our hope, that there is some xy that's going to satisfy both of those equations, and that's what's going on here. The answer here, I've got my answers here so I can keep myself honest, is A, and let's see how we get that. In the ordered pair, if the ordered pair xy is the solution to this system above, meaning some x and y fit both of these, where x is the same in both equations and y is the same in both equations, what is the value, and this should be of y. Kind of mark that off. What's the value of y? That's what they're asking. So the question is, how do we solve it? We know how to solve systems of equations by substitution, by something called linear combinations, by guess and check, which takes a long time. But when you have answer choices, you can literally substitute those answers in there. So if I put 17 in for negative 17 in for both of these, I need to come out with the same x value in order for it to be a solution. Therefore, the same x and y satisfy each equation. That's what would happen if I put negative 17 in there. Let's say we wanted to review some old stuff, meaning we wanted to review some of the skills that we developed in algebra. One of the skills is to use the elimination method, which is to decide a variable, make sure that the equations are both in, I guess, standard form, or at least the x's are over the x's, the y's are over the y's, and everything is kind of lined up correctly. And then decide on which variable you'd like to get rid of. In this case, I'm going to get rid of x. To get rid of x, I personally am going to multiply this second equation by a -1. Some teachers tell you to subtract, which is totally fine. I like to multiply by -1 so we have additive inverses, so I'm never guessing whether I should subtract or add. When I multiply by a -1 on both sides of this equation, I end up with a negative x minus 2y is equal to a -12. By doing this subtracting or getting rid of the x, I'm going to be left with y, and I'm therefore going to solve for y first. So now I'm adding everything together. Those guys cancel out, which is what I expected. This is going to be a negative y. This is going to be 29 plus a -12 will be a positive 17. Here I see that y has to be equal to -17. All right, let's look at the next problem. Here in number 2, the answer is D. Let's see how we get there. So the graph of the system of linear equations above is shown, and in this situation, xy represents the solution to the system. What is the value of x minus y? Well, when we talk about the solution to a system, what we are talking about is where x and y meet, or where they both satisfy both equations. So what you want to see is that point, I'll circle it so we can be really specific, that point is the solution. Can we name that point? Well, in that point, that xy point is going to be 3, -1. And I like to make sure I've got the numbering right, 1, 2, 3, yeah, and -1. That feels good, because you'd hate to make a silly mistake when you were dealing with something so simple as basically figuring out what the ordered pair is that refers to a point. The next thing we're going to do is take the difference of x and y. 3, x minus y would be 3 minus a -1, and I think you guys know that the answer is 4, as we said. Pretty straightforward. Let's look at this next problem. In number 3, when you're asked to find the value of something that's an expression given some equation or expression that you have before, know that this is a situation that's kind of contrived, and you're going to be asked to manipulate the equation so that somehow you're going to get 3a minus 2b. So what I'm doing is I'm looking at these guys and I'm trying to see what I have. What I'm going to do is I notice that a and b are together on the same side. I want to do that with my equations. I want to put a and b together on one side with one equation and a and b together to see if there's something I can do with the two equations to make it 3a minus 2b and hope that I have a numerical answer on the other side. That's really the only way to approach this. So as I look at this first one and this second equation, I'm really going to do exactly what I said, move my a's and b's to one side and my regular number to the other side. And so when I do that, I can throw my 6a over to this side, and I get a -6a plus 5b is equal to 16. And I'm going to do the same thing over here. I'm going to throw my b over to this side, my b term, so I end up with this. Now, sorry about that. Now I'm going to take these two terms and see if there's something I can do with them in order to get this. And so I'm actually going to put them on top of each other. Let me do that in a more slick way. So if I grab this equation, move it over here, and then grab this one and move it right underneath it, is there anything I can do with these two equations in order to get that, at least on one side? And I see that simply if I add them together, I can get that. So when I add these two equations together, notice I get 3a minus 2b, and I get a numerical answer on one side, which is negative 4, and therefore my answer is B. Here in number 4, your answer should be D. How many solutions does the system above have? When we're talking about two linear solutions, two linear equations as these are, you can have a couple of situations. One is where you have one line and then another line that will never intersect. In this case, you'd have 0 solutions. We know when we have lines like this, they're called parallel. Parallel lines have slopes that are the same. So one indication that you have parallel lines is that the slopes are the same. But when you have parallel lines, or when you have the situation where the slopes are the same, be careful, because you could have two lines that are actually overlapping one another, meaning you have the same line. In this situation, you have infinitely many solutions. Here, when we have two lines, we have no solutions. Over here, infinitely many. In another situation, when we're dealing with linear equations and systems of them, we could have one solution. If they are linear, you can only have these 3 situations. You cannot have 2. Now, if they're not linear, if you had like a parabola or something like that, you could have 2. So how do I know what's going on with this equation, these equations? What I need to do, seriously, is to put them in a form that I like. Everybody loves y equals mx plus b, because having it in this form tells us so much about the equation. So I'm going to go ahead and put both of these in y equals mx plus b form so I can see what I'm dealing with. All right, so with some real basic stuff going on, you can kind of pause it and take a look at what we did. We solved for y in each situation, and what we see is that we're dealing with the same exact line. Thus, we have that overlapping situation where there's infinitely many solutions. All right, as we look at this one, the answer to this one is 10. An office has 27 employees. If there are 7 more women than men in the office, how many employees are men? So the question is about men. I'm going to use W for the number of women in the office and M for the number of men. And anytime we have a variable, we're always talking about a number, so it's not cool to say W is women and M is men, because that doesn't certify the fact that we're talking about numbers. All right, that's just my little quick aside. So let's set up 2 equations, because that's what we're doing in this section. An office has 27 employees. In this context, we're talking about only men and women, as you can gather from the actual problem. So I would say W plus M is equal to 27. And then it says there are 7 more women than men in the office. So if I were to put women and men on either side of an equal sign, how could I make them equal? What would I have to do? If there are 7 more women, in order to balance out, I'd have to add 7 more men. Or I could think about this as subtracting 7 from women. Now that I have my equation, I am good to go. I'm actually feeling like I'm going to use another method and not linear combinations or canceling out as we've done before. I'm going to do substitution. So substitution is a situation where we take one variable and we isolate it, not erase it. That's not what I meant to do. When we isolate it, and I'm going to highlight the W and say I'm going to replace this value for W into this next equation. So here's what it would look like. I know that W is equal to M plus 7. So in the first equation where there's a W, I'm actually, instead of putting W there, I'm going to put M plus 7. So in a way, I united both equations together. All right, so now that that's done, I'm going to join like terms. 2M plus 7 is equal to 27. And with a few short strokes of the pen, I can see simply that M is equal to 10. And notice how I wanted to solve for what I was looking for. I could have figured out a way to solve for W, but that would not have led me to the answer. So the answer is 10. This problem, though it's in the medium section, is very similar to the last one. And by the way, the answer is C. Let's get started. So I'm going to start off with A being the price per adult and C being the price per child. Notice my variables have a numerical value. You know that there's a number attached to that. So we find out that for 2 adults and 3 children, so for 2A plus 3C we paid $14. If each child's fare is 1/2 of each adult's fare, so that means the child's fare is equal to half of the adult's fare. What is the total cost for one adult and one child? Notice they added a little bit of a wrinkle. They didn't ask me to solve for C or A. They wanted the cost for one child and one adult. So we're going to have to solve for both variables and add them. So in the end, I'm looking for A plus C. I'm going to use this equation and I'm going to solve by substitution. So my equations together will collapse into, notice I'm going to replace C in the first equation with C is equal to 1/2 A. This gives me an opportunity to have the equation in one variable, which is very simple for me to solve. So now I have 2A plus, this is 3, not 3.5, but 3 times 1/2, so that I can write that as 3 over 2A equals 14. I don't like fractions, so sometimes I just multiply by the denominator, so I can multiply by the denominator that's giving me a problem, or the greatest common denominator if I had several, and I end up with 4A plus 2 times 3 over 2 is just 3A is equal to 28. Simply put, 7A is equal to 28, and I get that A is equal to 4. Again, that's not my solution. Look how they have it nicely there, right? All waiting for us to get all happy that we solved the problem. But we're very smart. We know that A plus C is what we're looking for. So if A is 4 and we're told that C is half of A, that means that's 2. That's how we get the answer 6. This problem is similar to the first one that we dealt with, where I could actually go through, choose some values for y, and see which ones yield the same value for x, or I could choose one of the methods that I use for solving systems of linear equations. And, by the way, the answer will be D. So let's see how we can do this. Now, we've got a couple of things that we can do, but honestly, nothing's looking really easy because these fractions are making me feel uncomfortable. I could plug away some numbers, as I mentioned before, but what I'm thinking is, since y is isolated here and y is isolated here, let's set both equations equal to each other, solve for x, plug back in, and get our value for y. I know it sounds complicated, but to me it feels like the most comfortable thing to do. Otherwise, I'd be trying to do some systems of cancellation, and I'm not sure that that's going to be appealing to us later on. So what I'm going to do is set them equal to each other. So 1/5 x plus 4 is equal to 3 over 7x minus 4. Solving for this guy should be pretty simple, maybe. So I'm going to move all the x terms to one side and all the constant terms to the other side. So when I do that, I am left with 1/5 x minus 3/7 x is equal to a -8, and that's me subtracting 4 on both sides. I need a common denominator here. I can't get around it. So my common denominator will be 35. So because 5 and 7 both go into 35. So when I divide both of these, or when I get my new numerators, I'm going to have 7x, that's 7x over 35, minus 15x. Over 35 that I'm uniting together over 35. Is that all right? And then if I continue on with that thought, 7x minus 15x is going to give me a -8x over 35 is equal to -8. Now, how do you undo a fraction? You undo a fractional coefficient by multiplying by its reciprocal. So in red, I'm going to show that I'm multiplying both sides by 35 over -8. What I do to one side, I do to the other. The beautiful thing about this, very contrived situation, as we see that all cancels out nicely on that side, it's actually going to cancel out pretty nicely on this side as well. Those guys cancel, and I'm left with x is 35. Not our answer, not what we're looking for, but the cool thing is I can plug it back in either equation and solve for y. I'm going to use the first one because it's cuter. Y is equal to 1 over 5 times 35 plus 4. These guys cancel, 7 plus 4. And just like we said, y is equal to 11. If you don't believe me, both would give me the same answer, 3 over 7. Let's look at this next one, 35 minus 4. 7 goes into 35 5 times. 5 times 3 is 15. So in essence, this is 15 minus 4, which again is 11. So for now, it's really helpful in this problem to get this answer, to put everything in slope-intercept form. Use your graphing calculator to graph, or graph by hand. If the first equation has a y-intercept of -1, then and its slope is going to be kind of like that. This guy has a y-intercept of -12, and it has a steeper slope, and we can see that it has its intersection in the first quadrant.